Today we're going to finish chapter 5, okay, and we're going to talk about gravity, we're going to talk about satellites orbiting the Earth. But when we talk about gravity here, we're talking about the acceleration due to gravity, which is indicated by what variable? Big G or little g? The acceleration due to gravity is little g, okay? Because normally the acceleration due to gravity at Earth's surface is equal to 9.8 meters per second squared. However, as you increase your distance from the core of the Earth or from the surface of the Earth, what happens to your acceleration due to gravity? It decreases. As we get farther and farther away from the Earth's surface, our acceleration due to gravity decreases. And so today we're going to focus on being able to calculate that acceleration due to gravity at certain distances from the Earth's surface and things like that. So we're going to start with our equation, our universal law of gravitation equation. Okay, so we're going to be able to determine exact acceleration due to gravity on the Earth's surface using big G. Okay, and we're going to walk through this equation until we can have an equation to solve for the acceleration due to gravity rather than the force due to gravity. Okay, so we're going to start with this equation right here. This doesn't necessarily need to go in your notes, the whole step-by-step process, but I'm going to just show you how our equation gets to our final product. Okay. So we're starting with our universal law of gravitation equation, in which we take the force due to gravity is equal to our gravitational constant times m1, m2 over r squared. We're going to assume that one of the masses is of the mass of the Earth, right? If we're trying to find the acceleration due to gravity and the force due to gravity on the Earth's surface, or slightly above the Earth's surface, that means we need to use the Earth as one of our objects, okay? So I substituted me here for m1. Okay. Next thing we're going to do is we're going to substitute mass times acceleration due to gravity, or m times g, for our gravitational force. Okay, this is a substitution that we should know because when we worked with our forces, we know that Fg is equal to mass times gravity. So all we're doing is substituting m times g. And why did we choose m2 here? What do you think? Yeah, m1 is mass of the Earth. So m2 is mass of the object, which is what we're trying to look at here. We're not comparing it of the Earth. We're comparing it wherever this object is sitting at. Okay? So we're going to take m2, which is the mass of our object, whether it's the mass of a man or floating, whatever that we're looking at here, but it's the mass of our object. Okay? So we're going to take m2 times the acceleration due to gravity. And lastly, we're going to cancel m2 on each side. So that means we don't even really care about the mass of the object. All we really care about is mass of the Earth, radius, or how far it is from the core to our object, and the acceleration due to gravity. So this radius right here, r squared, we want to make sure that we make a note. This is distance from the center of the Earth. Oops, from the. Okay, so if something tells us they're sitting on the surface of the Earth, that means we know that r is just 6.38 times 10 to the 6th. Okay, but if it's at a position above the center, above the surface of the Earth, we would have to add that to the radius of the Earth. Okay, we always want r to equal from the center of the Earth to wherever our location is. Okay, so this equation is one that you will need in your equation sheet. This is one that we'll use a lot today. Okay, these two are kind of just steps to get there. You still need this equation like from last class. Okay, so top and bottom equations here we need. Okay, so if I would ask you to solve for the gravitational force at blah, 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 which equation would I use, the top or the bottom? The top. If I asked you to solve for the force, that means I'm asking you to solve for F sub g. If I asked you to solve for the acceleration due to gravity at one of these locations, which would I use? Top or bottom? Or one in between? Which one? bottom, right? Acceleration due to gravity is little g. Okay, so if you need to make that note in your notes to make sure you understand acceleration due to gravity is little g, I would go ahead and do that. Okay, anytime it asks for acceleration due to gravity, we're looking at an equation that involves little g. Okay. All right, we're going to go ahead and try some here. What's the acceleration due to gravity on the top of Mount Everest, which happens to be 8,848 meters above the Earth's surface? Okay, we want to find acceleration due to gravity. First of all, can you anticipate that the acceleration due to gravity is going to be higher than 9.8 or lower than 9.8 at a distance 8,848 meters above the Earth's surface? We think it's going to be lower than 9.8 meters per second squared, right? As you increase your radius from the center of the Earth, your acceleration due to gravity should decrease. Okay? So, first thing that we need to do, since it says above the Earth's surface, we need to take our radius of the Earth, which equals 6.38 times 10 to the 6th meters, and we need to add it to this distance. Okay, because what we want to do is we want to find the acceleration due to gravity at a location on top of our mountain that is 8,848 meters above the radius of the Earth. And we want our radius to be from the center of the Earth to that location at the top of the mountain. Okay? So we're going to add that together, which gives us that many meters for our radius. 6,388,848 meters. From there, all we're going to do is plug these numbers that we have into our acceleration due to gravity equation. Okay, little g equals big G times mass of the Earth over r squared. Okay, so mathematically, make sure we square this whole bottom term, the whole radius. We'll take 5.98 times 10 to the 24th divided by that. We multiply that whole thing by 6.67 times 10 to the negative 11th. And we get our acceleration due to gravity equal to 9.77. Yeah? We want to be careful not to round this up to 9.8, right? Because we want to make sure that we can see a difference. It's not a dramatic difference between the surface of the Earth and 8,000 meters above, but we do want to be able to see that difference. So be careful about rounding there up to 9.8, because then essentially it looks like we have no difference. Okay, we want to be able to see that difference. So just be careful about rounding there, but 9.77 shows us that there's a little bit of a difference. Okay, if gravity on a hypothetical planet is 3.21 meters per second squared, and the mass of the planet is 4.12 times 10 to the 21st kilogram, what's the radius of the planet? So here we're not working in terms of Earth. We're not going to use the mass of the Earth here. We're going to use the mass of this hypothetical planet. But our big G, our universal gravitational constant, still works. Okay, so big G still works even though we're working with a different planet. Okay, so what does this value tell us right here? 3.21 meters per second squared. What variable does that give us? Little g. Yep. And our mass of our planet is 4.12 times 10 to the 21st. That means we're going to just plug into our equation mass of the planet. I'll just put m sub p over r squared. All right, so mathematically I would move this to the other side first. And that would leave me with 4.81 times 10 to the 10th equals 4.12 times 10 to the 21st over r squared. And what do I do when I have a situation that looks like this and my variable's on the bottom? I'm going to switch these two places. And that leaves me with r squared equal to 5.86 times 10 to the 10th. When I square root that, I'm going to get my radius equal to 2.93. Perfect. And what's our units here? Meters. Okay. Good. So since we solved for the radius, where can we assume that this gravity is located? Is this above the planet's surface? Is this on the planet's surface? Where can we assume that this gravity is on the planet? Above or at the surface or below, or what do we think? Yeah, it has to be on the surface, right? Since we solved for the radius of this planet, which goes from the center to the surface, and it's telling us that at this radius we have an acceleration due to gravity of 3.21 meters per second squared. That must be telling us that at the surface on this planet the acceleration of gravity is 3.21 meters per second squared. Okay, that means we're not looking at anywhere above the surface or below the surface. It's exactly at the surface. Okay. Okay, we're going to talk about satellites that orbit the Earth and what they look like while they're orbiting and how we can find the velocity, the centripetal acceleration of that satellite. Okay, so we're gonna walk through a couple of our different equations here to kind of get us into a state of mind that we can work with these satellite equations, because they're a little bit different, a little bit manipulated, a little bit of a combination of a couple of different equations we've gotten so far. Okay. So satellites that travel in a circular orbit, we can use this equation to find their acceleration if it just gives us basic information like its velocity and like its distance from the Earth would be its radius. Okay. However, rarely do we get that type of information. Okay. More often than that, we have to dig a little bit deeper. Okay. So I'm going to kind of click through this here because my equations don't come up for a while. All right. So this is going to walk us through all these equations until we can get to our satellite equations down here. So I'm going to talk through this just a little bit. When we're talking about satellites that go in a completely circular orbit or orbit the Earth in an exact circular pattern, we can use our centripetal acceleration equation. If we want to find the force holding it in its orbit or its centripetal force, we can use either of our force equations here. F sub r equals m times a. Right, mass of the satellite times centripetal acceleration, or we can use mass of the satellite times velocity squared over r. Okay, all of these equations should look familiar to us, right? We're just using the mass of the satellite. However, since it's the force due to gravity that's holding these satellites in their orbit, right? There's a force due to gravity from the Earth on this satellite that's holding it in its circular orbit, holding it in its circular path, right? There's no string attached to it that's holding it in its orbit. There's nothing that's holding it besides the force due to gravity. Okay? When we look at things that are spinning in our normal circular motion problems like this, we normally have a string that's spinning it or an axle that's spinning it. Here we don't have anything holding it in place except for the force due to gravity. So we can combine these two equations, okay, by saying that F sub g is equal to F sub r, right? Our centripetal acceleration is equal to our centripetal force is equal to our gravitational force, because that's what's holding that satellite in place. So all we did here is take F sub g and set it equal to F sub r, or our centripetal acceleration, and we used our universal law of gravitation equation and our centripetal force equation. Okay, do we see why that kind of comes together? There's nothing holding that satellite in place except for gravity. Okay, so essentially your centripetal force and your gravitational force have to be equal to each other. Okay, from here, algebraically, we can cancel out the mass of the satellite on both sides of our equation and end up with equations that look like this. Sorry, that kind of took away some of our stuff. End up with equations that look like this. G times mass of the Earth over r squared equals v squared over r. Or we can substitute for velocity 2 pi r over t. If we aren't given the velocity of the satellite, if we're just given the period of it, we can have 2 pi r over t. And we square that t, and we square this term right here because velocity has to be squared. So these are two equations that are specific for satellites. Okay, so when these go onto your equation sheet, these are really our only two new ones here. When they go on your equation sheet, they need to be stipulated that these are for satellites. Okay, and essentially these are the same equations. We just did a little substitution here. Determine the height above the Earth's surface a satellite must orbit in order to stay on the same point of the equator during its entire orbit. We call this a geosynchronous satellite. That means it's moving at exactly the same speed as the Earth, essentially. Okay, as it's rotating, it's got a point that's fixed on the Earth, and it's going to rotate. Not necessarily at the same speed because the radius is different, but it's going to orbit so that it's looking at the same exact point on the Earth the whole time. Okay, and we call that a geosynchronous satellite. Okay, so here's our equation for satellites, and our overall goal is to find the radius because we want to find the height above the Earth's surface. Okay, so essentially here we want to find r. Are we really given anything else in our information? No, they don't tell us anything else. We do know the gravitational constant. We do know the mass of the Earth. We're solving for r, but we don't know the velocity of the satellite. Okay, which means we can't use this version of our equation. We have to use this version. Okay, so since we don't know the velocity, we do know the period. Okay, we know how long it's going to take for it to make one complete revolution around the Earth. Since we decided that it's traveling with the same proportion as the Earth, right, same proportional speed as the Earth, it's located at the same spot on the equator the entire time, so it's going to rotate essentially in one day, right? The Earth makes one complete revolution in one day. Do we all agree with that? It makes one complete spin. I'm not talking like laps around the sun here. I'm talking about one spin, right? One day. So that means that T must equal 24 hours for the satellite. If it's going to travel at the same proportional speed to the Earth, T has to equal 24 hours. So how many seconds are in 24 hours? Since our time has to be in seconds. Right? 86,400 seconds? 86,400 seconds? Okay, so that's going to be our T that we can use here. So I'm going to go forward a slide here so I have a little bit more room. But this is going to be the period of this satellite. Okay, it can make one complete revolution around the Earth in 86,400 seconds, okay, or 24 hours or one day. Okay, so now we're going to basically just plug in some numbers here and solve for R. We know that T is equal to 86,400 seconds. And this is going to take a lot of algebra work just because there's squares and there's rearranging that we're going to have to do to solve for R. So I'm going to go walk through it kind of slowly, but just make sure you ask questions if you have them. All right, so G is 6.67 times 10 to the negative 11th times mass of the Earth over r squared. And we're solving for r here. We're solving for the distance above the Earth's surface. Okay? I'm going to go ahead and distribute this, that square. So it's going to end up 4 pi squared r squared over r times 86,400 squared. Okay, I want to make sure that you understand only t is squared on this bottom part because of the velocity equation, right? V is equal to 2 pi r over t, and we need v to be squared here, so we square the top term and the bottom term for velocity. Are we on the same page so far? Okay, we see where this 4 pi squared r squared came from? Okay. Now, do we see anything we can do right off the bat? Yeah, we can cancel at least here, r, right? We can cancel an r right here. And I'm sure there's more ways that you can do this, but that means I'm going to get rid of r squared and I'm going to get rid of r. So I'm left with an r on both sides. Okay. So now there's a couple different ways you can go about this. I'm going to get rid of my denominators. Okay, I'm going to do my best to get rid of my denominators, which means I'm going to multiply by r squared on this side, and I'm going to multiply by r squared on the right side. I'm going to do the same for this 86,400, and I'm going to do that on both sides. So I want to multiply by 86,400 squared, and multiply the left side by 86,400 squared. That's just to get rid of my denominators. Again, there's multiple algebraic ways you could go about doing this. Okay, I'm just walking through my method. I'm sure it's probably the least efficient of all, but you know, that's how my brain works. So that at least leaves me with only numerators, which I like. 4 pi squared r times r squared, which, what is r times r squared? R cubed, so I'm going to simplify that. Okay? So do we see where this whole term came from? I got rid of my denominators. That's how I'm working through it. Okay, so my whole left side of the equation I got to equal out to 2.98 times 10 to the 24th. And that's all going to equal 4 pi squared r cubed. So now my next step is going to be divide by 4 pi squared. Divide by 4 pi squared. Which leaves me with 7.54 times 10 to the 22nd equals r cubed. So now in your calculator, if you hit math and you scroll down to, I think, number 4, it has cubed root of something. So we want to take the cubed root of this number. Do we agree with the 7.54 times 10 to the 22nd? I'm running out of room here. What do we have a radius equal to? Times 10 to the 7th. Okay. However, when we look back at our original problem, what did it ask us? Above the Earth's surface. And what does this radius value give us? This gives us from the center of the Earth to the orbiting satellite. So what do we need to do to find the distance above the Earth's surface? Subtract out. So we need to subtract out here minus 6.38 times 10 to the 6th meters. And I'm still running out of room, which means our distance above the Earth's surface is So that means this particular satellite is orbiting at a distance 3.59 times 10 to the 7th meters above the Earth's surface. Okay, so it takes a little bit of time, takes a little bit of work, a little bit of algebra skill, and like I said, I'm sure there's other ways to go about solving for that R, but, that's how I do it. This asks us now, at what speed would the same satellite be orbiting? So we want to find velocity here for that particular satellite. Okay, so we can use our simple uniform circular motion equation to find the velocity. So v equals 2 pi r over t. Here's an important observation. What's t here, first of all? $86,400, right? It's still going to go one complete revolution at the same speed as the Earth. So 86,400 seconds is 1 day. So t isn't going to change here. What radius do we use? The total. And so what's the value of our radius? Good. 4.23 times 10 to the 7th. Okay. The reason we use this total radius, not the distance from the surface of the Earth, is because our radius should always be from the center of the Earth to the position of our satellite or position of our object. So that means velocity equals 2 pi times r over 86,400 seconds. Okay, and I get about 3,068.9 meters per second. Yeah?
76.
You got 76. Okay, I used 4.22 times 10 to the 7th in my original equation, so it's going to be a little bit different. Okay, but around 3,070 somewhere. Okay? I used 4.22 times 10 to the 7th and not 4.23. Okay, so that's it for Chapter 5. Satellites and acceleration due to gravity were the last thing. Your book goes over something called Kepler's Law. We're not doing Kepler's Law, so we're going to exclude that part of Chapter 5. So that is the end of Chapter 5.